Yeah, so you think of what happens with an and yeah, you get the right number. Has anybody worked on find best yet? This is the one that I get the most questions about, find best. Okay.
I haven't touched it yet.
Okay.
Even I haven't started working on it.
Okay.
I've had problems making a freaking virtual machine in freaking stupid thing.
Oh.
Apple Swift.
Yeah, something for Nina's class.
Oh yeah, yeah. I've been hearing a lot about Swift lately. It doesn't seem to be progressing swiftly. And given that the due date of this one's November 17th or September 17th, I'm not particularly surprised that nobody really started that. I'm glad you're working on one of the functions. So now you're like in the lead.
Yeah, I also started on the sort where you wanted to copy the array and then sort it on the heap. So I'm trying to figure out the heap sort part for that.
Oh, I don't think you have to use a heap sort.
Because it says you use the heap on there.
Well, for storage, you don't have to use a heap sort. These two parameters, the function to make a copy of the array, sort the copy, and return a pointer to the sorted copy. So you have to make a copy on the heap because you can't return a pointer to something that's on the stack frame that's about to go away. So you got to use malloc and make some heap-based storage. But there's an algorithm called heap sort that's completely unrelated to this question. You don't have to use it.
All right.
Yeah.
That makes things easier.
Right. Heap sort is a perfectly fine sort, but it's somewhat complicated to implement.
All right.
So use whatever algorithm you like.
Yeah, that's what I did yesterday.
Okay. Yeah, well, if you got heap sort working, then you did a trick that other people won't get to learn from this semester. That's good, right? Because after all, the more little parlor tricks like that you learn, the more impressive you'll be in the job interview. Because you can be like, oh, this is just that question you asked. That's a lot like implementing heap sort. Okay, so any other questions on Project One? Don't worry, people aren't working on Project One. They're not asking because they've all finished. They're asking because they haven't started. Okay, let's talk about kind of finish off last time talking about counters and closures and returning stuff and that kind of thing. And then we'll talk a little bit about a couple of the minor C topics and then we'll move on to kernel modules. Okay, so last time, back out of here. I think I typed CD public HTML as my password. I realized that afterwards. Okay. And incidentally, CD public HTML would be a pretty good password. So if anybody ever got it with a keylogger, they think it was a command.
Maybe a copy.
Okay. So anyway, so the last time we were working on this returning stuff things, and I should probably reintroduce it. And I should actually get this right one of these days. There we go. Okay. So, you can see our examples directory is getting rather fuller. This is getting closer to the point of the semester. I have to work strongly when everybody's looking at examples, figure out project one. When everybody starts asking, how do I figure out what example went with which day? And the answer is very simple, but you have to have clicked on the right thing. And so let's go click on the right thing. Okay. So if I go to the first web page and go to examples, we've got these. We've also got last modified. If you click on this, you can actually sort it either direction by last modified date. So then if you're like, okay, I was looking at the notes and I saw that we were talking about this topic on the 28th. Then if you look in this sort of list, you look at the 28th, here's the examples that go with it. Only caution I might add on this stuff is sometimes people see that all the examples are posted, all the notes are posted, and so, why take notes? And then everybody gets into a little bit of trouble that way because there's plenty of stuff that's not in the notes or the examples, you see? So it doesn't quite free you from the note-taking burden. But I see various people with notes and pens and things open, so I think you all get it. Okay. Yes, closures and that sort of stuff. So at the end, we had a function that we were looking at returning something with. But I'll just go ahead and kind of start this one over since it was just at the very end last time, and that was on the other side of the screen. Okay. Okay. We'll return a counter. set up a return counter dot CPP. I'll show you how this works in C++ 2014. Perhaps you did this in 3.12, but perhaps not. I don't know. I think 3.12 focuses more on the like normal things that normal people do, and less on the unusual edge cases. Okay. So we'll have a. Actually, this is now. We'll just go ahead and stick with the printout stuff. Okay. So the C++ one here will have a function that returns integers. So inside main here, we're going to call this function. It's going to be a counter making one. We'll call it make counter. So we're declaring it normally. Let's leave this part off for a moment. We'd say make counter, and it's going to take an integer which shows where the counter starts. Okay. So that's how we do the declaration normally, except I left off the return type here because it's complicated. Inside main, we want to say that we're going to have a pointer to a function, and it's going to be our counter. And so the type of this thing, again, it's complicated. It's a function that doesn't take anything, but it returns an integer. So to say that, we say we're going to have a reference to a function that returns an integer and takes nothing. And so we'll get the value for it from mk counter. This number here will be where the counter starts. We'll start counting at 5. So then after that, we should be able to say something like this. Okay, so you'd expect this one prints out 5 and then 6 and 7 and 8. Maybe one more than that. Depends how you find a function. Okay, so every time we call counter, it increases its count, it returns us a one higher number. I'm really looking forward to teaching 3.12 because I have all these ideas of what everybody must have learned from 3.12, and I think sometimes I'm right, and sometimes I'm like totally wrong. So once I've taught it, I'll know what people learned in 3.12. It's going to be good. I'm going to be a better teacher for this class and other ones like networks. Okay, so anyway, here's the STL, Standard Template Library. Sound familiar? Okay, you got it. So it must sound familiar. Okay, so the Standard Template Library has some cases where you iterate through lists by having a thing that returns. It's called an iterator object. And every time you call a function with this that's associated with this iterator object, it gives you the next thing in the data structure. So you repeatedly call it, iterate through it. Now, the reason that I was wondering if everybody is, if you're the only one who's showing the enthusiasm, is because that might have been just kind of an edge note, because in C++ 2017, you can iterate through collections in a much simpler and less convoluted manner. Where you just say like, use a kind of a Python style loop, where you say like auto something colon, whatever the collection is you're going through, and you go through one at a time. Oh, I'm getting better agreement with that. Okay. Well, if I was teaching 3.12, I would show you the new way too. So anyway, back in the old days, we had to get back a thing called an iterator, and we call a function that uses back differently every time. Anyway, this counter works a little bit like that. So every time we call it, it goes a little further. Okay, so this function up here. So that's how we have it, except for this, return type. Can we say auto there? I don't know. Maybe we'll say auto. Let's not say auto. So we're going to have a function that returns an integer. And so then this thing here, we're going to get a function reference back to it. Okay, counter takes an int a, and then the function that comes back from it doesn't take any parameters. Okay, I think that might be right. Okay, so we're going to have to find a function in here and then return it. Now, this is a C++ file here, so we can't say int counter and then define our counter function here and then say return counter. Can't say it. Because this is C++, we're not allowed to have a nested function. So even if we could say exactly what we want to say up there, not allowed. Okay, so we have to do instead is return a reference to this counter function. So if we say, let's just go ahead and make our counter up here. Well, I'll just return it like this. Okay, so we're going to make a reference to this thing. We have to use a lambda function. I think I am going to attempt to say auto here and just see if it works. And if it doesn't work, then it doesn't work. And we'll be okay with that. Might even say auto down here. Okay, so we're going to return a lambda. So a lambda function, C++, we can define it like that. So the first one is the captures. And this is the part that's going to get convoluted. Yeah.
Your second auto variable needs a name.
Good point. Okay, so we want to have something where we add to it. We want to say like something like return a++. So we'll increase the value of a there. Now it started out whatever it is, and we'll return a new value. So that's what we want to do. But if we try to build this in C++, it's actually going to give us a little bit of a gripe beyond the autos, which you might not actually write stuff. Okay. So it says error, A is not captured. Okay. So the lambda's function specification, it looks a little bit convoluted because a C++ lambda has these three parts. So C++ lambda. You don't actually say lambda anywhere, unlike Python. So this is the captures. This is the parameters. This is the actual body of the function. That's where your code goes. Okay. So we're not taking any parameters. That's our counter function doesn't take any, so we're okay there. But we need to talk about these captures. So we put an A there and capture A. It's going to change what C++ says, but not necessarily in a completely good way. All of our errors went away except for this one. Error increment of read-only variable A. Okay. So you can't just capture it like that. Now if we say ampersand A, let me see, this may make it completely go away. It did. Okay, this is a capture by reference. So let me pull up the chart real quick here. Oh, let's see if our program works first. Okay. Oh, not quite. Return A++. Not sure what we got back. It wasn't okay. Counter 5, it should have been what A is. Let's take off A++ and just see. Oh.
That's for counter.
What's that?
Isn't that where counter 1 would be? This is me spitballing, but possibly where counter 1 is being stored? No.
That somehow should be fine. We took it 5s, yeah. Oh, you know what? I think I botched the capture specification. We're going to need to look at this table. Okay. Captures. You got a comma separated list of 0 or more captures, optionally beginning with a capture default. So that's what we're looking at with the captures. And then it's got a number of other ones here. By the way, this is coming in C++ 20. I haven't reviewed the C++ 2020 standard, partly because given that it comes out in 2020, which clearly must be 100 years in the future because it sounds like it is, it probably hasn't been fully stabilized yet. And even if it has, it's probably not available in current compilers yet. So I just haven't found it an interesting exercise. But it's going to come with this template parameter list thing, which lets you make like template lambda functions. We'll see how those come out. Anyway, capture specifications, references. Okay. Oh yeah. Capture types. So you can have a few different types of captures. You can implicitly capture it by reference, or you can implicitly capture it by copy with an equals, or you can not say anything at all. Let's say equals. Okay. So it didn't change a thing there. We were apparently already capturing it by copy. Oops. So if we say that, it's still going to be giving us the exact same error. So that's one option. You can say by copy. You can say by reference. When we did it by reference, we got kind of a weird answer. We got the wrong number in there completely. Here's a few different ways you can, is that readable? Here's a few different ways you can specify the capture. You can say that we're going to capture by reference by default, like that, or you can capture particular things by reference, and you can capture, some things by reference, except for this one's captured by copy, or all manner of other possible things. That's reference type capture. Okay, so we're capturing by reference here, and we're capturing by reference. Let's put it right back here. By reference. Let's see what happens again. No, still a problem. Okay. Well, now everybody else understands it too, and nobody's told me what I'm doing wrong this morning. So
That number it keeps spitting out is boggling me.
well, it's the top of the range, like top of, this is top of the 16-bit range. Yeah, that's an unusual answer there. Okay, so I think what we'll do is cheat a little bit, because I actually did this earlier to make sure it was going to go off, okay? Slower, more carefully. Okay, so CPP files that I have here. Right, cnt.cpp. Oh, mutable. That's what I'm forgetting. Okay, let's fix it first.
A declaration that you can actually change it, that's not read-only.
Yep. Okay, that works fine. Okay, so yes, mutable. Forgot. Yeah, I think I actually put that in my notes because I knew I was going to forget. Nope, didn't. Okay. Okay. Yes, you have to say mutable before you can change the copy one. So once you set it's mutable, then you can get back a reference. So let's go ahead and demonstrate this thing actually works right. I'm going to go ahead and make counter 2 as well. And counter 2 is going to start with a higher number. It's going to be in the 500s. And so then here, we'll go ahead and say, let's see what counter 2 is. And we'll increment counter 2 a few times. But then, at the very end, we'll go ahead and do counter 1 again. And we'll see if counter 2 has managed to override counter 1. Okay. So, there we go. That's counter 1. That's counter 2. Okay. So this is an example of returning a function with a variable that is captured. So once it's got the captured variable, we're all good. We got an instance of that, and we're fine. It makes it a little bit of a convoluted piece of code doing this, of course, but thankfully we had auto, so that's good. Okay, let's try and do this in C. Okay. Yeah, actually. C. Okay, so we can't use that anymore because we're using C. If we try to run this in the C compiler, return counter C, you can see we've got a whole list of problems. And it starts with the fact that the whole lambda thing does not make any sense at all. Okay, so what we need to do is define a nested function to try to make this work. So, oh yeah, and we got to change this prototype up here where it's going to have auto. Anyway, so if we say up here int counter, and it doesn't take any parameters, and then at the end we're going to want to say return counter. Okay. So this one is really pretty simple. So we want to do something a lot like this, and that would take that parameter A and then give us back a reference to it. Okay, so next we should probably complain about the use of auto. I would like it if they added auto into a warning function definition declared auto. Return type defaults to int. Isn't that interesting?
You'd think you'd be okay with it then. That's not.
Well, it's not going to be for other reasons other than that.
Wasn't that interesting?
Says it's defaulting it, but it's
Okay, now we should have a kind of an error right here. You okay with that? I don't know. Let's do that. Oh no, type defaults in. Okay.
yeah, it won't default to a flow.
So I've had the experience a number of times giving a lecture on either C or C++ and proclaiming that it cannot do something and then finding that it can because it's been added to the standard. We recently had an update on the C standard. I think we're compiling with C 2011 instead of C99 or C89, which we used to use. And so that always leaves the possibility that I didn't notice that in the standard we actually added auto or something like that. So that's what I was checking. Okay, but it doesn't seem to be there. I was surprised by that. It acted the way it did. Okay, let's take this and make it not auto. Okay, so we'll have a reference to a function called mkcounter, and mkcounter takes int a, and the thing that it returns, okay, doesn't return anything. It doesn't take any parameters. Okay, that might be okay. So then these ones we have to change the specification the same way. So instead of declaring counter one like that, you have to declare it like that. Okay. Counter 2 can be declared the same way. That can't happen. Okay. So let's see now. Return counter. Let's see. Hey, look at that. Not even a single warning. But what happens when we run it? Oh, isn't that interesting now? So it worked.
It uses counter 2.
But it used counter 2 the entire time. And you can see up here, we clearly just said A++. We didn't say if it was counter 1 or whatever. We got the latest value of the counter. Now, as it happens, we're actually a little bit lucky we made it this far. A up there is a parameter to mkcounter, so it's got a spot on the stack. The spot is relinquished as soon as mkcounter finishes, because the stack frame goes away. Now, the second time we call mkcounter, A gets allocated in exactly the same spot. Not a real surprise here. Computers are very consistent about doing the same thing from time to time. So we end up replacing that spot with a 500 when we make counter 2. Now, here's where we sort of lucked out. When printf ran, it didn't overwrite that value with anything, even though it was beyond the end of the stack. And so this call to counter could have potentially overrode it. And actually, so could the call to printf, since we built 2 stack frames on here. But neither of them actually wiped out our value. So we were actually okay, oddly enough. Okay, so that becomes, anyway, so this counter 2 overrode it. So it didn't quite work right. I'd say, well, what if you do something different here? What if in here you say something like this? Okay, we'll take this, we'll say we make a static int b, and that's initially initialized to A, and we do B right here. Let's try it. Initializer element is not constant. Yeah, that could actually be a problem. So making a static int here, let's make it equal to 0, 0 constant. Okay. Segmentation wall. That's very far.
Hey, it's Alex's famous results.
A static variable gives you a variable that stays like one copy for the function. It makes like a global variable that's restricted in scope to that particular function, so you just have one copy. But in the case of making a nested function here, it doesn't quite work the right way.
I don't like it.
So I might say, okay, what about the static variable here? Okay, and then when it's called, we'll say b equals a. Okay, and we'll say this starts out with 0. Okay, so then we'll use b. Sure, you got it now. So yeah, you can play this game with a few different things, but basically, wait, why would we get a semicolon there? We put everything back together the original way, right? Did GCC it? Oh yeah, there we go.
Yeah.
Okay. But yeah, so you can play this game trying to do this, but the basic problem is since MK counter has a stack frame that goes away after it's called, you don't really have a spot to put anything down here. And so everything keeps getting lost. Okay, and so the mechanism the C++ is providing with the closures is a way to tell the compiler, okay, yeah, sure, it's in the stack frame. A is part of the stack frame. A is about to go away. But we want to capture it with this nested function. So then the compiler goes and squirrels it away somewhere, probably wherever global variables are stored. And then it's maintained for us until we're done with our function. So if we wanted to do that, we could squirrel it away somewhere else. So for that, we would have to come up with a somewhere else to do it. So we got that there. What if we said something like this? We'll say, I'm going to have trouble storing my memory address here. Yeah, that's not it. I'm looking at a solution involving malloc, but I think most of them are going to end up with a problem of a different sort. Unless we had like a global variable.
That's what I was thinking.
But we need one
Outside.
global variable per counter that's been returned from MK counter. So MK counter is going to need some sort of global data structure. Here, we can do this. Okay, and counters 10 equals 0, 0, 0, 0, 0. Let's have 5 counters. Okay. Okay. So then we just have to say, we have to find an empty spot in our counters. Let's go ahead and declare I at the head. Let's say it's CNT index. There we go. Counter index equals 0. And I'll move this along. IDX is, we'll use while here, while there. While CNT IDX is less than 5. Okay. So if counters at CNT IDX counter index say this is not true, so it is 0. Okay, so we found a 0 in our table, then we've got it. Okay. That's the successful
I like the idea of go-tos. Other people are like, that's just terrible programming conventions. You're not supposed to do that.
Okay, so where we don't find one, if we go through the whole thing, oh, we got to increment CNT IDX. Okay, if we go through the whole thing and we don't find one, sorry, no more counter spots. 0. Okay. 0 is a good error value for this, because normally it returns a memory address of a function. So it returns a 0, that's very clearly an error. Okay, if we've got it, counters at CNT IDX is our current counter that we're about to use. Oh, now we're going to have another problem now. Because how do we capture that inside the counter? Because we're running back into the same loop here, right? So here we'll finish this, and I'll get to the problem. Okay, suppose this equals whatever we're supposed to start at, A. And so then here, we want to use our counters. Counters at CNT IDX plus, like that. But now we need our counter index captured. You see where we're running into the exact same trouble, right? We couldn't capture A, and we can't capture our counter index. So we're kind of stuck again. We could, for example, require a reference. Okay. So then we have to have this parameter come back. And at this point, this doesn't have to be in here. It can be here. And then what we return isn't actually the counter, it's a counter index. Okay, and this would be counter 2 index. Okay, so then we, instead of this, we say counter. We don't say which one. We just say counter 1 IDX. for the ones that are counter 1. So those are counter 1. Those are counter 2. Let's grab one of this. Okay. Perhaps that works. Oh, we got to return C and X. Got some warnings. We went to there. That should be fine. Oh, right here. That's the call. Okay. Makes pointer from integer without a cast. Yeah, it doesn't return this convoluted thing anymore. Now it returns an integer. Okay. And this is what was it saying that happened? Int warning type of CNT. Oh yeah, that's actually fine. That's a good default. So it looks like we don't say the type in C. It defaults to int and gives you warning. Okay. Yeah, it works. So I guess the whole point of this is to explain what the whole closures thing is in C++ 2017, and finally that you don't have it in C.
That was a lot of convoluted stuff to make that small statement.
It kind of was. But anyway, so yeah, now you probably understand C++ 2017 a little bit better. Okay, so that's that, and that's the difference between a nested function and a lambda function, which comes with closures and that sort of thing. And so that's one of the main things that C is lacking that C++ has. Okay. So let's move on. Structures and memory layouts. Just kind of a quick note on this. Okay, so if we make a structure, and let's go ahead and declare a struct here. Okay, struct stuff, and so let's say the structure has an int in it, and it's got a char, and it's got a size t, 64-bit integer. That's thing C. Okay, so I got 3 things in this struct. So down here in main, we can make one if we want. Okay, so then we can say our stuff.a equals 5, our stuff.b equals 42, our stuff.c equals, say, 64. Okay, and so that's all set. Okay, so I'm going to just stop here on line 15 and debugger. Right, 15, run. Okay, so right there, the return 0. And I actually did this in a little bit of a silly way. Let's go ahead and rectify that. Okay, so there's our program there. Okay, so since we're stuck right here in the middle of our program, we should be able to print out any of those values. Sure, piece of cake. Okay, we should be able to print out the addresses of these things. So if we look at the address of our stuff is located right here on the stack. So if we look at our stuff.a has the same memory address as this struct stuff. This is because these things are typically allocated starting with the first one and ending with the last one. And so A is at the beginning of the structure in memory. So if we wanted to print A, sure, we could say print our stuff.a. Or, you know, we could also just say print out our stuff. If you print out our stuff, it shows you the entire list of its contents. The star here is the ASCII character. That's ASCII character number 42, since B is type char. And if we said, let's print out our stuff pretending it's an int, it's 5. Because that's where the, int was. So if we go ahead and take our stuff.b, and that should be the 42, and print out the address of it, you can see the address there is an A4.
So that makes a lot of sense. We got an address here, 0x whatever, A0. This one's at a bunch of stuff, same stuff, A4. So we move on 4 bytes. That's how big an integer is, 4 bytes. And we get the next one. Okay, let's look at C. Now, here's where everything goes a little weird. You see we moved along 4 bytes again. We moved from A4 to A8. But you can see clearly that B is of type char. Char is only 1 byte. So we move along 4 there. And so if we print out, it's at our stuff.c, of course, it's 64. That's what we put there. So everything's actually good except for these 3 bytes. And you look at it and say, well, what happened to our extra 3 bytes there? It just seems to have totally disappeared. And the answer is that the structure is laid out on 4-byte boundaries on x86 64 architecture because the architecture is faster at addressing in 4-byte increments. So that's what happened there. Okay, so it's been optimized for speed instead of anything else. Okay, let's edit our program again. .c. Okay, I think what we have to say here is this. If I remember right, let's see. Okay, that's not quite it. I have it in a bunch of demos in other places. Figure that for a moment. Okay. There. Oh, double parentheses. Of course. How could I forget? Okay. So we'll go back to doing that again, and there we go. Okay.
Is that just the convention that they use, or is there just
This
reason
is
behind the double parentheses?
this is not a standard extension to C. It wouldn't necessarily work in Visual Studio or Intel C compiler or other C compilers other than GCC. So if we go ahead and do this, here, right? Oh, yeah. I was trying to GDB it. That's not what works. Okay, run, print the address of our stuff.a, our stuff.b, our stuff.c. Why is it that? Okay, so you can see, we ended up in a different spot here. That happens, sure. The stack addresses are not guaranteed to be anything in particular. But if you look at the offsets, we went from 3 to 7 here, going from A to B. That's our 4 bytes. Good. Then we went from 7 to 8. And so now we didn't waste any space. Okay, so this the attribute pack is a way to do that. That can work fine. Here's another thing that can be done. Suppose we had a char D right here, and I realized we didn't. So if you did it like this and didn't have packed, then B and D would both get aligned to 4-byte areas, and we would have 2 3-byte areas that were missing. You see, and weigh 6 bytes. However, if we instead define it like this, it doesn't change a thing in terms of how we use the struct. However, it saves us 3 bytes, 4 bytes actually, because instead of having 2 3-byte wasted areas, we've got those packed into the same area, even without the packed attribute. It'll put multiple chars in the same one without aligning it like that. Oh, weird. Yeah. Okay. Anyway,
So would that be anything like when I've defined variables in a lot of things, I don't do I don't do 1 variable per line. I do all the same type of variable on a single line. Yeah, like that.
Yeah.
So that would do the same thing with the memory.
That's equivalent to that.
Okay.
The only difference is it's plus typing.
Okay.
Okay, so that's where structure packing comes in, both making the compiler do it by just making it not include gaps,
and manual structure packing, where you carefully arrange everything so that there aren't any gaps. So, good C memory management trick. Okay, you see some structures in the kernel set up both ways, and so I'm going to explain what packed is for. And packed can also be used in the, I pulled the example out of the networks class. The reason that the example was in the networks class is if you're receiving just a bunch of binary data in a row from a network socket, and you're going to read it out, then one thing you can do is take whatever you read, put it in memory somewhere, say that the pointer to the beginning of it is actually the pointer to a structure, and then just address the structure members in order to sort out this, big blob of data you've got. I don't know what to call it when it's unorganized. Anyway, and so that's what we use for network stuff. Okay, so that's structures and memory packing. Okay, so next topic, kernel modules. Okay. So all this memory stuff kind of comes together with the kernel module and how the kernel module is implemented and that sort of thing. So the operating system has a lot of stuff to do. One of the things that your operating system needs to do is handle device drivers. Hi there, you're using a device driver. Alex is watching from the
Or
virtual
will be.
thing there. Well, okay, will be.
In the future.
So,
Like I said, this is all going to end up going up on YouTube and
right.
just have the link be passed around.
So, what operating system are you running?
Windows 10.
Windows 10. And did you compile the kernel? No, you can't. Microsoft won't give you the code.
Yeah. I was going to say no. Of course not.
So, we got Windows 10 here, and we've got Alex watching virtually, and he's using this device here, which I probably shouldn't touch.
That would be a good idea. Because
And,
it took me half this lecture to get it lined up right.
yeah, and the device there is interfacing with the operating system. Now, the developers of the kernel at Microsoft may well have been aware of the existence of this device, but they also might not have. Let's say Logitech, I'm sure they have Logitech webcams, but if you look at Logitech's list of webcams they produce, they got a list as long as your arm of different models and makes and this, that, and the other thing. And they probably all work a little bit differently at the hardware level, or they wouldn't have that many. Now, that said, they probably use the same unified Logitech driver package. This has been a major trend in drivers lately. And by lately, I mean the past 2 decades. And so the way that works, I'm holding a video card here. Video card. And so this card I'll have a manufacturer, and I'm having trouble determining which one it is actually. If it's AMD or NVIDIA. Neither of those actually make the card, they just make the board. VGA card, NVIDIA International, there you go, it's got an NVIDIA chip on it. So when NVIDIA distributes a driver package these days, they just distribute one driver package, and you don't have to find exactly the right one, you just find the one that fits all NVIDIA cards. And so then there's a kernel module that gets loaded from the NVIDIA driver. We're going to break something, but let's do it anyway. Who cares? Let's do it up here. No, let's not do it up here. Let's do it in my office, and I can fix it down there if I have to. Okay, probably won't let me finish anyway. Okay, NVIDIA. Somewhere in here I've got, there it is. Okay, it scrolled past really quick. But I've got this NVIDIA driver package right here, NVIDIA, Linux, whatever. So, if I run that thing, for some reason it's not auto-completing, but that should take care of it. Okay, it'll decompress this NVIDIA Accelerated Graphics Driver for Linux x86-64. And yes, I am running an X server. And yes, it would probably make all sorts of chaos happen if we pull a video driver while the graphical user interface is running. Unfortunately, I have to agree with this warning. Installation has failed. Okay, well anyway, if it had continued, it would have compiled an interface to the kernel, a kernel module. And if we look at my modules I had listed, if you look at LSmod, it shows you the ones that have those are in there. And we graph for NVIDIA. You can see I've got a number of things stuffed into my kernel related to NVIDIA in order to run the NVIDIA graphics card that is in the machine. Back to the point of the developers of Windows 10 might or might not have been aware of that Logitech webcam. In this case, the developers of the Linux kernel do not know how the NVIDIA video card functions because NVIDIA won't tell them. In fact, NVIDIA distributes their driver as a closed source and compiled binary. And what you have is enough source code to compile an interface between your binary driver and whatever kernel you happen to be running. And if you look at the log of messages that comes from the kernel and grep for NVIDIA, you actually type grep, you'll have a number of things that come in here related to NVIDIA Unix kernel module, et cetera, et cetera, et cetera. But one of them, right here, NVIDIA module license NVIDIA taint kernel. So the reason our kernel is tainted is we had an open source kernel where if you suspected that the NSA had engineered a backdoor into your operating system, you could sit down and read the source code. Maybe done in a decade, but you could do it. The fact is there's people that review the source code quite regularly, and so there's probably enough people maybe somewhere to even find it if there was some kind of backdoor. That's the idea. But now I've gone and compromised the entire thing because I took a binary compiled set of code from NVIDIA and stuffed it into my kernel. So now what did NVIDIA do to my computer? I don't know. They could have put their own backdoor into it. Maybe they're busy digging through it, trying to find all my pictures.
What's your credit card number?
Yeah, they're gonna have my credit card number, and they're gonna know all that I have chickens because
They're gonna take control of your chicken coop.
Oh no, they might make the door flap.
NVIDIA's guillotining my chickens.
So the NVIDIA kernel module is now in there. Now that's the tainting message, but the reason I put it there is since the kernel module developers don't know how my GTX 760 works, NVIDIA does, NVIDIA can give me some code that makes it work quite nicely, and then I have 3D acceleration on my computer. Good deal. The fact is we hand over our life history to various companies for various reasons anyway, and so whatever is one more. Okay, so so that's in there. So that's what kernel modules are for. I didn't have to recompile my kernel in order to put this module into the kernel, and I can't compile that module anyway, and so it's fine. Same as up here for Alex's benefit, the Windows 10 kernel couldn't be recompiled, and so we've added this kernel module. So here's the trick. So normally with a C program, you have all your files, and you compile it, and you link it, and then it's all together, right? And it works. And you don't add stuff to it after it's compiled. If you wanted to change a line of code, you recompile it. So with the kernel, we don't even have to turn it off. We can keep running it and add to it. So the way this works is with static memory addresses. It's got basically a table of symbols and where they're located. And so the last bit of linking on your kernel module doesn't happen until you actually put it in the kernel. And then it gets linked with memory locations that are already in use and active and have contents. And then everything begins running. Okay, so that requires a certain awareness of where all this stuff is located in memory, but luckily most of those mechanisms have been taken care of more or less for you. These have been around since Linux version 1.2, so it wasn't originally in the kernel. Originally, if you ran Linux in the very early days, if you got a gadget, you'd have to recompile your kernel, and there probably wasn't a device driver for whatever you just bought, so you'd have to write that too. And so things were a little bit more hands-on back then. Reasons for using these things. Debugging is pretty handy. I think that's actually maybe the original motivation. If you're going to keep trying to make something work, you can have a non-functional but non-computer crashing bug. Something where it's like, oh, it's supposed to turn the webcam on, but actually it didn't for unknown reasons. And then you have, versions, 1 through 97 are all, it doesn't turn it on for unknown reasons. That way you don't have to recompile your kernel and reboot every single time. I haven't done a lot of device driver writing, but the one device driver I did write we had some trouble because some of the documentation for the thing we were writing for was actually quite incorrect about how you control it with a register. And so it took a fair number of compiles before we figured out what was going wrong. Okay, so that's one reason. Yeah, debugging and recompile less often, and reboot less often altogether there. Okay, they're not slower. Once they're in, they operate at full speed. And so you're not giving up performance by not having it there. The only reason you might give up any performance is when your computer originally finds some device. If the device requires a kernel module to be loaded, then the operating system will have to go find the kernel module and load it. So just there's that. Okay, the kernel's smaller. So in this particular case here, the kernel module for the webcam can stay around on this computer, taking up hard drive space, but not memory space. So if Matt were to turn this computer off and bring it home and not plug in the webcam, he wouldn't have to use any memory for the driver for the webcam until he plugs it in again. So that's another advantage of using these things. And then you can reload a particular driver without rebooting. And so theoretically, at least, I could replace the NVIDIA driver on my computer without rebooting it. I would have to shut down the graphical system because the graphical system is making heavy use of the driver. Okay, but you can do that. If you push like Control F1, then you get this login prompt. It'll work on any Linux machines around the room. And right now we're not using the user interface, so I can log in on here. I realize it's hard to read, and I realize I probably typed that wrong because it's taking forever. I try to type passwords faster than I type anything else, and so I actually make more typos in passwords than other things. Anyway, so once we're in here, we can say something like sudo service. I think we're running light VM stop. And I'm not going to run that right now because it would shut down the GUI, and then I couldn't switch back to it. I'd have to re-log in and go find all the notes, all that kind of stuff. But if I ran that command, it would shut down the graphical user interface. It would leave our terminal running just fine right here.
Really?
Yeah. And at that point, we could probably pull the NVIDIA driver without any consequences.
So if you're actually manipulating the NVIDIA driver, how's it that you're getting any display at all?
When you're doing it like that with a terminal, it's operating like it's kind of a base level late 80s VGA card.
Oh, okay.
It basically uses almost nothing to do that.
Yeah.
Well, for a moment, I was thinking it'd be something that was on board and either the motherboard or the processor that still has some kind of base capability. To
Could
do
very
that.
well be using the onboard video to do that.
Well, the monitor's plugged into the GTX 1070.
Yeah, that's why I was like,
there's no onboard video.
Yeah.
But weirdly enough, even the highest end video cards still come with the capability to act like a late 80s VGA card. And your BIOS expects that. That's how BIOS draws its screens.
That's what I was curious about that.
Your BIOS is blissfully unaware that your card is capable of so much more.
Well, it makes sense though, because it's got to have that base thing, base stuff built into its chips. Otherwise, it wouldn't post. It wouldn't fire up. You'd have to
I mean,
load
it very well could post, but you wouldn't be able to access BIOS to change things.
You can actually start up a motherboard with a processor and memory in it without a video card installed. In some cases, they'll halt on an error. In some cases, if you push the right keyboard button that you won't know about because you can't see anything, you can get past the error.
Usually it's F1.
Yeah. And so then at that point, you could actually start up a system and SSH into it or something potentially. It's very rare for anybody to run a computer actually without video card. Even servers have basic video cards you can plug in a monitor and see what's happening.
But usually once you've got the server up and running, you unplug the monitor and then run it through.
Actually, software has been plugged in full time, but it just runs to a big KVM switch that gets turned to software like once a year, if that.
The wonders of server room KVMs. Those are fun to play with.
The one over there has like a weird keyboard, like it's kind of constrained in its width, and so it's got keys in funny spots, and it's got terrible feedback.
Yeah, I wouldn't be surprised.
I should sort of hate that one. And then when you use it, you got all the servers around, like playing the vacuum cleaner song in the background. And it's cold in there, of course, because it's air conditioned down to server levels, and
it has to be.
It's really a pretty unpleasant spot.
I mean, the server room back where I used to work, we had it had its own separate air conditioning in addition to the building air conditioning to keep it about 10 to 20 degrees colder than the rest of the building.
Right.
And we had like 3 different KVMs that we used throughout the time I worked there because one broke, one burnt out, and then we finally had another one that was actually 2 KVMs linked together for all the various servers that we had running.
Yeah.
Interesting.
Yeah. Yeah, this is a pretty common way to set up the server room doing that. A software also has a serial link that's not plugged into anything that would allow you to do the same thing from a more comfortable room.
Most servers have that.
Yeah.
A lot of servers have. Well, yeah, I mean that is the serial link technically.
So why not kernel modules? For a while, I didn't like kernel modules. I don't really have a super good explanation for why I didn't like them. I just didn't. So I'd actually build my kernel. I used to compile it all the time back then, so I didn't have any kernel modules. I'd actually build it without the module interface. And so then you just build everything into the kernel that you might want. And then if you get a new device, you recompile your kernel.
It sounds like excessively difficult and pointless.
Yeah, I use them all the time now. But anyway, you can do that if you want to, and that works fine. You have to have a management system of some sort set up for hot plugging devices, which you don't have to have if you're not using any kernel modules. And basically what it does is you plug in the gadget, it goes and finds it. So your friend brings a webcam and they're like, hey, look what I found at a yard sale. And you're like, oh yeah, let's plug that into my computer and see what happens. And then it'll have to search through its various catalog of stuff. Yeah. Yeah, you find out somebody has set it up with that. You can get this device. Don't anybody buy one of these things unless you want to. You plug it into a USB port, and it charges off the USB port, a capacitor, and then it sends a high voltage surge in through the data lines and takes out your motherboard.
Oh, one of those.
I've heard about that.
Yeah.
Yeah. Yeah, if you buy one, just don't even bring it in here.
Hacking tools.
Okay, so these are used for device drivers, of course, because there's a whole plethora of hardware. File systems actually is a reasonably common way to do it. You don't necessarily want your main file system there. If you put your boot file system in there, it gives you a chicken and egg problem. If your kernel module that says how to control your file system is on your file system, then you can't read your file system until you have your kernel module that tells you how to read your file system. You see where you could end up with a problem here. Yeah, you're perfectly welcome to come in if you want. There's plenty of seats in here. That's not a very good candidate. But other file systems. Suppose, for example, you don't have an Apple machine. You're running Linux, and you're running it on x86 hardware, and you don't expect to ever have an Apple machine. But you think that maybe sometime you'll find like an Apple laptop and you'll have to take a hard drive out and read it. Sure, go ahead. Make yourself an HFS, hierarchical file system, kernel module, store it on your hard drive. It takes like 50 kilobytes. And if anybody ever brings you an Apple laptop and they're like, yeah, so I had this thing and I had this accident.
I don't even think they use that
I was
file system anymore.
driving my car and I drove it into a ditch. And then I took my laptop out to save it and I accidentally dropped it in a stream. And I should have left it because actually my car stayed dry inside. Do you think you can read my hard drive? You can take their hard drive and plug it into your machine and it'll go find the HFS module and maybe it'll work.
Didn't Apple stop using that file system?
Oh, good point. They might have. Well, whatever they use now then.
Because I think when they changed to OS 10, they started using a more logical, not so stupid file system.
Yeah.
Relaxed on their proprietary crap a little bit.
No, they didn't relax on it. They made their own different.
APFS.
See,
Apple
they made their own
File
they're
System.
a different one.
Everything you need to know about the new APFS. And it actually happened on
10.3.
Yeah, well,
iOS 10.3. Sorry,
Mac OS
10.12, which is
that's like more recent.
that's a really recent update. That's High Sierra.
Yeah, that was post cat names.
Yeah.
So yeah, that's actually
That came out last year.
Yeah, and I think it succeeds HFS Plus maybe.
I think it's HFS. Yeah, it's right there at the top.
Okay.
HFS. It aims to fix core problems of HFS Plus.
Yeah, so HFS Plus must have been introduced in '98 with 8.1.
That's the one they've been using for ages.
And they used it all the way up into
OS 10.
10.3. Well, 10.7 and up had transparent encryption.
Yeah.
They're using this thing up until recently.
Wow.
Yeah, it was.
I
it's
bet you a lot of you that have
previous.
Macs have this thing on it.
But yeah, the original HFS file system has been outdated for quite some time.
Okay, you can add system calls to it. We'll talk about system calls some other day. Network drivers for various protocols. You can do that too. There's kind of a basic set of protocols everybody uses these days, like IPv4, IPv6, TCP, etc. But if you want to support one like unusual ones, you're like, well, this is my laptop, and someday I may find myself locked inside a building where they're actually using an older, they're using Apple Talk, and I'm going to have a Linux machine, and so I want to be able to use Apple Talk on my machine so that I can figure out where, how to hack into the doorway systems and unlock them so I can get out. Sure, kernel module. Contingencies. Okay. Executable interpreter, sure, you can add more. Now, executable interpreters are kind of difficult projects. So if you say you decide that what you're going to do is write an interpreter an interpreter that executes exe, like DOS files on Linux. If you get it working, then you could make it a kernel module and add extra formats. Probably an easier target here than a DOS exe would be like a FreeBSD executable, for example, or maybe OSX command line executables, something like that. The thing is, most of the ones that are easy, people aren't very motivated to do, because the ones that are easy are the other ones for POSIX compliant systems, because they're going to have the same system calls inside the other executable format, and so you have a fairly simple format conversion. But if that's the case, you could just recompile it and it would work. I do know of one case where somebody's done it. FreeBSD has an interpreter for Linux binaries. Compile it on Linux, run it on FreeBSD. FreeBSD also has its own binary format that you can compile to, and that's the standard one and everything on its compiled form. The reason they did that is Linux is big enough now that there are proprietary, non-recompilable programs. So if you wanted to run like Skype or something on FreeBSD, you can download a Linux binary for Skype, not the source code, a binary. And so then that way you could run it on FreeBSD. The problem they keep coming up with is that the FreeBSD developers are very idealistic. And so, for example, on Spotify depends on some other libraries for rights management kinds of stuff that FreeBSD has been reluctant to allow on their platform. And so even though you could take the Linux binary and run it, it would find a lack of other libraries and not actually continue onto the functioning part. And that's actually the main reason I haven't tried FreeBSD on my main machine. I have a FreeBSD machine down there. I like FreeBSD quite a lot, but it doesn't run Spotify. So.
Most important program.
Okay, so inserting modules. You got a couple of commands for this, insmod and modprobe and whatnot. So we've got a computer. Let's look at this one. Okay, let's say lsmod. Here's this computer, and it's got all of these modules in it. I want to pull one that causes only minor chaos. I want to be fairly limited. But
So you don't want to blow up the whole system?
I wanted to do something. We got a USB human interface device thing. What am I plugged in with the keyboard? The keyboard is PCMCIA. Okay. So, monprobe-r USB human interface device. Okay, should be out. The mouse has ceased functioning. Because we don't have the USB human interface device driver. And actually the cursor's also disappeared, oddly enough.
Yeah.
Well, I don't have any mice plugged into the system anymore. And if I had a PCMCIA mouse, I guess I could unplug the keyboard and plug it in. Do I have a parallel port? No, we don't. There's no parallel port mice anyway.
There's
there might
also
be a
no
serial
parallel
mouse back
ports
there,
anymore,
but-
really.
Yeah, I don't have a serial port, I'm hearing it. Okay, but the reason I checked carefully to make sure I wasn't operating a USB keyboard is I wanted to still be able to talk to the computer.
Without
Okay,
having to
so let's
reboot
put
the
it back
silly thing.
Sudo modprobe USB HID. Okay. Hey, look at that. It works.
Huh.
So
That's
we're
pretty
all
cool.
back.
Turn on and off like
Yeah.
that.
Oh, yeah, I mean, when you pull the driver for the USB human interface device subsystem, then nothing works.
That actually gives me an idea for something.
I hate dealing with
So,
older motherboards and you're trying to get into the BIOS and.
here, we'll give
have
another
USB
example.
support.
See this thing here, E1000E? This is a PTP here is using E1000E. The E1000E would be our Ethernet driver. It's driving our gigabit Realtek, I think.
It's our
Ethernet
network.
board. There's E1000E. Okay, so you can see that the network works. If we say ifconfig, you can see we've got a eno1 here with this IP address. Sudo mod probe remove E1000E. Okay.
Now you have nothing.
Unknown host. If we look at ifconfig, we're there. If we say ifconfig-a, that shows us all the Ethernet adapters on the system, whether they're configured or
Which
not.
is local only.
Yep. The only Ethernet adapter we have is the local host one, which will allow us to talk to ourselves if we'd like to.
Allows us to be
Yeah,
crazy
very
people.
nice. Okay, so we can put this thing back. We just say mod probe it in here, and then if we say ifconfig-a, you can see it back, and hey, look at that, we've got our Ethernet address. The reason that the Ethernet address is back, we're running a DH client daemon, which is managing this stuff behind the scenes for us. And so the daemon will automatically try to reestablish a connection, for example, if we bring it down. And it would give us a new DHCP lease if something changed. But it can't do anything about it if the network card disappears. But once it's back, it can put things back in order for us. And it did.
I still think it's funny how it's always still registered as a separate card, even though they're not anymore. They're part of the motherboard.
Separate chip.
Mhm.
Yeah, it's just a matter of whether you take the interface and, if you took a PCI slot and, you put something in it and then carefully remove the plastic surround and solder all the pins onto your card, it doesn't really change anything in a logical sense. That's essentially what they did. A little bit of more creative routing than that. So you can take the modules in and out, and that's what happens. So, tools up there. I started at the very bottom using mod probe. Mod probe is what you use for modules that are already installed in the system, and it's a complicated enough program that it will go find the module if you referred to it by name. It's got directories it searches for this. Insmod up at the top is simpler. Insmod won't go out and find it. If you have it sitting there as a file in a directory and you say insmod, whatever my module is, then it will attempt to put it in. It does have a few safeties on what it will put in. This is like cars. If you take your car and your car uses gas, we will suppose it does, gasoline, petrol as the Brits call it, because most of them do in this country, and you bring it to the gas station and you try and stuff the diesel nozzle into your tank, unless it's a pretty old one, it won't go. The reason is, since the unleaded days, the unleaded nozzle is actually smaller than the regular nozzles were, and it won't fit through the screen in your tank. Now, the opposite does not apply. If you decide to fill up your diesel truck with gasoline, it will fit. And if you have an old vehicle that uses regular, like my truck used regular originally, but it was upgraded with hardened valve seats and whatnot, now it takes unleaded, because you can't get regular anymore. For good reason, it was poisonous.
Well, I mean, unleaded is still poisonous, but
right. But see, I don't have the unleaded screen in it, and so you can put the diesel nozzle in my truck. And it has mud flaps the previous owner put on because he thought they were cool, because they say cat diesel power. So I loaned my truck to somebody once, and he filled it up with diesel. Because it said diesel power in the back, right? The diesel nozzle fits. And then he called me, and he's like, your truck is running really bad and smoking a lot. And I was like, oh, well, I'm sorry. It's a cranky old beast. I'll try to get by and, take a look at it later. But he was trying to move, and I was somewhere I couldn't go look at it. And so his brother took a look, and his brother's like, wait a minute. It has spark plugs. So unfortunately, I didn't save him any time at all on his move.
Is this the truck that's broke down up in?
I fixed it this weekend and brought it back.
Oh.
It wasn't all that broke down. The secondary float was stuck, and it was leaking fuel into the back of it, which was making it run super rich and making it die at idle. It also would have got horrible gas mileage if somebody had managed to keep it running.
Yeah, I would have.
But no, it's back in my driveway. I got to go buy hay for the goats. Yeah. Okay, so RM mod, RMod looks pretty bad, like it's gonna go delete your module or something, it won't do that. All it does is pull it out of the kernel. It'll stay around in your file. It still requires like a moment hesitation before you run it. It's like if you take some gadget that's waterproof. This is waterproof. And so if I turn this on and I'm gonna drop it into a swimming pool, you know, there's like a moment of getting over that we don't do that kind of thing. I have a waterproof video camera, and that one's even harder to put under the water. You're just like, close my eyes. Oh, okay, it's under.
It looks like using a GoPro in bad weather. It's like,
Yeah.
you know it can do this. It's designed to do this, but you really still don't want to.
Yeah,
just
yeah.
because.
Anyway, that's RMod. You can totally use RMod. DepMod will show you dependencies between modules. Incidentally, if you do LSMod, it actually shows you that information as well. DepMod gives you a different view of it. If you do LSMod, I showed you LSMod. This gives you a list of the modules that are currently stuffed into the kernel, and it's got a size here and it's got a use by. So this module here, FAT, file allocation table, is used by the modules MS-DOS and VFAT. Don't know why it's actually in the kernel, but it is. Okay, so then you got mod info NVIDIA. Okay, so that just gives you some information about them. There's the version, there's you know, there's license, revisions, aliases, and stuff, you know. So it gives you information about it. Okay, we inserted them and removed them, and we'll talk a lot more about these and build one and stuff it into the kernel next time, because we are out of time this time. So have a nice day, everyone. Don't let me go this way.